WebAssign? Good, okay. Now you should join up for WebAssign if you haven't already. This Sunday you've got your first set of assignments to get done. It's essentially chapter 3. So you got a lot of work to do to get done this Saturday, 3.1 and 3.2, this Sunday I should say, 3.1 and 3.2. And you've also got this file at the top called Getting Started with WebAssign, which basically just takes you through how to do the various features that WebAssign has. In my version, you may not see a picture quite like this because I have a different version of it, but there is an ebook, and if you click on it, it's just like a textbook, but it's online. You can read through it and you can get information. If you want to do an example of a question, if I hit this thing here, in my case it says view, you won't get the same choices. You go boom, and I don't know if you can do that. Can you see the questions now? No, okay. Well, what you would get is you would get the questions. Now, I'm going to nip it over. Are you now being able to see Math 99 from Canvas? Oh, good, that transition worked well. Canvas is where all the resources are. WebAssign is where your homework is and where your test is. So you go into WebAssign, that's online homework, right? They ask you a question and there's an answer. And if the answer is X is 10, that's what you kind of write down, right? It's a little box and you put in 10 and it automatically grades you. And you get 3 shots for each one and you work your way through, and that's where the homework is. You'll have one midterm exam and that'll happen on week 4, Monday of week 4. I think it's the 20th of July off the top of my head. And then you get a final, which is I think a Tuesday, August or something. Can't remember the number, but you can look it up. And that's your final. So you only have 2 exams to worry about, although they're very big exams. The midterm's worth 20% of your grade and the final's worth 30%. So just those 2 things on their own are going to be worth 50%, half your points. You're going to get 30% from your homework. So that's why you have to make sure you do all your homework assignments to get the most points out of that. And there's a further 20% for turning up in class. That essentially means that every time you turn up, you get 2%. So everybody here has already got 2%. It's not bad, right? Just turn up, pay attention, you got 2%. Now, what do I have here? Well, I'm not going to get in and out all of this. That you've got the time to do it. If you look at the welcome one, it'll tell you a whole load of things that you need to get started up with. It'll mention, for instance, Zoom. The fact you're here means you know that. The fact you're here probably means you've already been to Canvas and at least seen some of the good stuff. I've broken the information, the things I give to help you into weeks. So this is week 1. So if I click on week 1, again, are you seeing chapter 3 lessons, or do I have to go out and in? Okay. If you go to this one here, it shows you videos. We can, just by the sheer way that the summer quarter is working, I wouldn't be able to go over every single thing as deeply as I'd like to. So these are really good resources. So for instance, if I don't do enough on what's called the substitution method and you'd like to see more examples or ways to look at it, here's a good little video. It only lasts 6 minutes. That's what this is about, right? 6 minutes and 9 seconds. Watch it. And it's always good to get different people's perspective and different ways of saying and doing things. So these are as varied, almost as varied as I could find. I tried to find the ones that were most relevant, and hopefully you'll use that resource. And that's what it is, it's a resource. This little placeholder here, when we finish this lecture, it'll probably take me well into tomorrow because I have to edit it. But I'll be putting our video, just like these videos, this video that you've got right now will appear here. So if you forgot or say, I liked the way he said whatever it was, I want to have a look at that again, figure out what he did, or I'd like to see how he worked through that example, then you can click on it. And you know how you can do on a normal video, you can jump to, the 35th minute or whatever it is, and you can see what it is. So that's what's going to go there. If I move to the PowerPoint, I don't know, can you see the PowerPoint thing? Now I'm on a roll with technology right now. This is basically from the textbook. It's a PowerPoint that kind of shows you some of the basic information from that section. So you can look through that. That's another thing. If we click on the last one, this is down here. This is the one I'm actually going to be using. And I don't know if, are you seeing chapter 3.1 Cartesian coordinate system? Perfect, okay. So I have notes of my own that I've put together that allow you to go back and, you know, look at things again, because you might not always pick everything up the first time, and it's kind of helpful if we have lots of different resources. So you've got videos of various people, you've got your Zoom lessons that are recorded, you've got a PowerPoint, and you've got my own notes. So there's 4 different major resources that you can use as you go through this, and hopefully between those 4 we'll be able to catch anything that didn't kind of make it, you know, didn't make sense the first time around. So far so good. Now there are 13, that's all, 13 classes. When we do the 13 classes, you're allowed to miss 3. So you can still get your full 20%, 2% a class, right? 10 classes. So if you have to go to the dentist one day, or you're called into work, more likely, at 5 o'clock class at least, you can still achieve your full grade. I suggest that when you miss a day, hopefully you don't miss any, but when you miss a day, that you use the recorded Zoom lesson and, you know, and go and look at it as if you were here, right? Okay, first things first then. We are going to look at how to solve what are called systems of equations. Before that, I'm going to do a kind of wind back and just make sure that we're all comfortable with some of the skills that you need to be able to do this. Really right at the beginnings, we all should be comfortable with how to plot points on what is called a Cartesian grid. That's the fancy name for that thing there, right? It's called a Cartesian grid. So if I wanted to plot the point -2, 4, do you see you go 2 to the left and 4 up, and there you are. You feel comfortable about that, right? Plotting points, no biggie. Here's a whole load of points all plotted, so you can just kind of use that as a refresher. Here's another thing that you need to be able to deal with. Hopefully you've remembered, or you've seen what is called the slope of a line. Right? A slope is a number that in a way tells you how steep a line is, right? A big slope would be really steep, and a gentler slope might be a half, a steep slope might be 4. Not only does it tell you that, if you slope up from left to right, as they do in this picture, it's a positive slope, and if it goes down the way this direction here, then it's a negative slope. So slopes can be positive or negative, and one way to get them is rise over run, which basically the rise is the vertical distance and the run is that horizontal distance. You could put the dotted line on this side if you prefer, rise and run. I look at it this way: if you start at this point, you do the rise first, and then you do the run second. So that's why the dotted lines are on this side. It kind of helps reinforce you get up out of bed, right? You rise, in this case, +8, and then you run another 6. And then you're always expected in mathematics to simplify fractions. And 4/3 is the correct answer. Don't turn it into 1 1/3. Although that might seem a better answer to you, it's not considered a good format in mathematics. When we talk about exact values, we mean 4/3, 17/5. You also are expected to simplify. So if you notice in this case, 8/6 would be simplified down to 4/3. Now, when you look at rise and run, slopes, that particular one here is a positive 4/3. Do you see this green one here, this line here, has a negative 4/3 slope? Can you see you go down 8 before you go along 6? How do I remember personally? if a slope is positive or negative, because sometimes you can forget. I imagine that you're traveling from left to right and that the green line is a hill. And as I travel from left to right, if I go uphill, it's positive. And if I travel from left to right and I go downhill, it's negative. So that's how I easily remember. Because most people can remember the rise over run, but they're not 100% sure, is it plus or minus? So that's one way of figuring it out. Now, if you have a horizontal line, then you get a very interesting slope. You get a slope of 0, which kind of makes sense. Could you imagine a horizontal line's got no slope to it? The slope is 0. So a line like, you know, that one there that's green, that line there, by the way, is called y equals 2. That would have a slope of 0. Now, vertical lines have a rather annoying slope. Don't know why that 0 is there, because it's not true. It's actually undefined. Because 8, oh, there it is. 8 divided by 0. That's what it is. It's saying the run is 0. Is undefined. Now, here are some examples of some random red lines. And let's just chuck out some questions. They're numbered, I think they're numbered 1 to 8. I don't know if you can, if I maybe make it bigger. There, that's as good as I can do it. Which one of those lines, any one of those lines, is positive slope?
2, 5.
I hear 5, right? Which, there's others, but 5 is correct. Negative slope?
6.
Yeah. 0 slope?
8.
Yeah, you don't have a choice. I think there's only one of those. What about vertical or undefined, I should say? Undefined slope?
7.
7. So we get quite comfortable now. I know this is refresh, but you know, we just want to get our brain into, you know, into mode. So you're comfortable about lines, positive, negative, what kind of slopes and what they look like. That's really what that is about. Here is a little bit of formal way. If you know the coordinates of 2 points and you want to know the slope joining them, then you use this little formula here called y2 minus y1 over x2 take away x1. So I am going to do that right now. Hey, where's that doing? It's got a funny angle. Right. Let's suppose that I have a point A and its coordinates are 5, 7. And I have another point B and its coordinates are 9, 11. And I want to find the slope of the line. We typically use the letter M to represent the slope, which really is weird. I would probably have used the letter S, you know, S for slope, but it's M. So can we blame the French? It's probably that the French word for slope starts with an M, right? We'll make that up as if it was true. So you can say slope, or even better, you can say slope with a little AB beside it, and that makes it even clearer, you know, which 2 points you're joining together to make a line that you're finding the slope of. The formula says y2 take away y1 over x2 take away x1. That is essentially the rise over the run. The reason why you need a formula is that you can't always plot 2 points on grid paper and then just count the boxes for rise and run. Can you imagine if the points were 57, 42 and 11, 239, you know, you'd never be able to plot those. So we need a formula. This means the y coordinate of the second point take away the y coordinate of 1. So imagine the first point is called x1, y1, and the second point is called x2, y2. So if you want to do y2 take away y1, it's 11 take away 7. And that will be your rise. And the x's are 9 take away 5. In this case, 4 over 2, which gives us a really nice answer, positive 2. We're comfortable with how to calculate the slope of a line if you needed to. So it's basically plug and chug using that formula. And you have to remember that the first point is called x1, y1, and that your second point is called x2, y2. And as long as you can remember that and the formula, you should be able to find the slope of any line that's joining 2 points together. Okay. Now, suppose I did one of these calculations and it ended up being this guy. What would that simplify down to?
0.
Which would be what? A horizontal line, essentially, right? And suppose you got that. What
4.
would you get? Would you? Think again. 4 on the top, 0 on the bottom.
Undefined.
Yeah. You remember, you're not allowed to divide by 0. It's bad news. That would, in fact, be a vertical line. So can you imagine most of the time you're going to get a number like 2 or 3/4 or -1/2. Sometimes it will be 0, sometimes it will be undefined. Let me try some out here. Does it matter if I have -7 in the bottom? Is 0 over -7 also 0? Yeah.
Yes.
Yeah.
And does it help undefined if that's negative?
No.
No. If you ever get a question and the answer is 0 over 0, what are you going to do? It's a trick question, by the way. You're going to look at the question again because you're wrong. You'll never get 0 over 0. Do you know the only way you could get 0 over 0? If someone went and said to you, find the slope joining the 0.14 to the 0.14. And that's silly, right? Joining a point to itself doesn't make sense. So you will never need to worry about that combination ever appearing, right? So you're either just going to get numbers that you can deal with, 0 on the top, 0 on the bottom, and we're cool. Any questions so far? We feel comfortable? Right, good. Let's go back to where I was a moment ago. And here, this stuff here, when you go and look at it, it gives you lots of help and examples. So I'm not going to go through every example, but you can imagine that you find the slopes of various lines. You can, in fact, tell things. For instance, see this one, AB and CD. Do you see these two lines here? If you look, I hope I've done this well. If you look really carefully, aren't these two lines parallel to each other? I mean, this one's a shorter line and this one's a longer line, but parallels get nothing to do with how long you are. Isn't it to do with what direction you're pointing? If two lines are parallel as they are here, won't their slopes be the same number? So if you have two lines and the slopes of those two lines are the same number, you can say that those two lines are parallel. And if you have two lines are parallel, they'll never cross. Okay? They'll never intersect, right? Like a railway line, right? They'll just travel forever, right? And never meet. On the other hand, if you have two lines that are clearly different, as you have here, you see that when two lines are different, they intersect. And when that happens, two lines, if they're ever going to intersect, they can only intersect at one point. Would you agree? There's no way in the world, if I continue drawing this line and I continue to draw that line, there's no way in the world that you're ever going to get another place where they intersect. Isn't that one where my mouse is pointing, the only intersection point? That's going to be helpful later on, because when we solve a system of equations, what we're essentially going to do is draw the straight line for each of them. And those two straight lines will cross, we call it intersect. And the point where they intersect, in this case, what's that, 2, 0? That's the solution to the system of equations. The coordinate 2, 0 tells you that the x is 2 and the y is 0, right? It tells you it's a solution. And if you draw the two lines and they look like this, that's going to say this question has no solutions. So an answer could be that the solution to a system of equations is there is no solution. So let's look at how do you draw sketches of straight lines. There is a number of ways you can do it. There's essentially 3 ways to do that. So I'll show you the first way. It's a table of values. So suppose I want to sketch y equals 2x, right? I got my square paper. You kind of need some square paper for this if you're doing them by hand. And you put down various x coordinates, probably numbers like -2, -1, 0, 1 and 2. And then in this case, the formula is very simple, y equals 2x. All you do is, well, okay, when x is -2, y is twice that, so 2 -2's get you -4, right? Nothing, 2 nothings get you nothing, 1, 2 them, you get what the y value is. And the y value is twice whatever the x value is. So for each x value in this case, the y value is twice it. And then if you look vertically downwards, can you see that you now have a sequence of points that you can plot? -2, -4 would be that point. 0, 0 would be there. 1, 2 would be here. And if you've done it correctly, won't all the points be on the same straight line? Right. If you do an equation correctly, and it's a straight line equation, if you plot them and 4 of the points are in a straight line, but that guy is, say, up here somewhere, that probably means that you've screwed up, and go and check your calculation. Right? It doesn't zigzag. Straight lines don't zigzag, right? They're one straight line all the time. Now, if you're going to do a straight line using a graphical technique, this is probably overkill. You probably don't need 5 points. How many points do you think you can get away with and still be able to draw the same straight line?
3.
Someone says something, but I didn't quite catch it.
3.
3. 3 is a good number, and that's the one I would choose. Technically or legally, whatever the word I'm looking for here, couldn't you get away with just 2 points? You know, if I know 2 points, if I join them together, won't that be the same straight line? Now, the person who said 3 was, well, was thinking the way my mind works. Why would you choose 3 if 2 will work?
Just to make sure.
Just to make sure. If you screw up and you only do 2 points, do you know you'll never know that you've screwed up? Because you'll have 2 points that you'll join together. On the other hand, if you do 3 points and you screw up, won't one of them not fit? The line, the dots will kind of be ziggy-zaggy. And so 3 is the go-to guy. Now, if you want to say, well, what x's do I pick? Most of the time, I don't think there's a problem. I would probably pick 0 as one of my x's. And a couple of reasons for that. The first one is, if you pick 0, don't you get the y-intercept, which is kind of useful. When x is 0, you get the y-intercept. And it's normally an easy number to calculate. I don't go crazy. I don't do 0, 10, and 55. I mean, theoretically, couldn't I use those as my x values? But I mean, doesn't that sound like I'm going to give myself a heck of a lot of work? So keep it small, keep it simple, right? Pick 3 x values, nothing 1, 2. Most of the time they'll work fine, right? If you want -1, 0, and 1, right? That chucks in a negative number. That's a good combination as well. Now, here is a little bit more complicated version. The equation of the line is y equals 3x take away 2. Here are 4 points, perfect straight line. Everything is good. Looks like my dog has decided to pay. One of my dogs paid us a visit. Come on, there you go. I think she wants to find out how to do linear equations. So far good. Another couple of things that you can use to check that you're drawing these things correctly. You see this straight line? If I choose, say, this point here and this point here, do you see these 2 points that I'm going back and forward from? Let's look at the slope. A rise of 3, a run of 1. Isn't that slope 3? do you notice that the 3 next to the x actually is the slope of a line? If a line is called y equals 2x plus 1, its slope is 2. If a line is called negative 5x plus 7, the negative 5 is its slope. So you can actually tell the slope of a line by using what we call the coefficient of x, the number next to x. Now, I said pick numbers like 0, 1, 2 for your x's, or negative 1, 0, 1 for your x's. Totally fine. Doesn't always work. See if the guy that you're trying to sketch is slightly ugly. By that, I tend to mean it's got fractions in it. You might want to adjust your x values. Now, I could certainly do 0, 1, and 2, and 2 of those points would work, and one of them would kind of sort of work. But what I choose to do in this kind of case here, if this is a fraction, pick x is 0, x is 2, and x is 4. Why do you think I'm picking those instead of nothing 1, 2? Yeah, anybody? Why would I choose those x's rather than nothing 1, 2? It's not a trick question. It's actually, once you hear the answer, you'll say, yeah, well, I kind of knew that. I just didn't think that's what he was asking.
They're easy to divide by.
Yeah, they're easy to calculate by, right? Isn't a half of 4 a lot easier than a half of, well, it's not that hard. But I'll show you an example where what I just said might make a little bit more sense. Because most people could probably cope with a half. It wouldn't really be too onerous. So let me invent a really ugly version of that same situation to show you why sometimes you may have to adjust it. So if you can bear with me for a few moments as I do my zoom in and zoom out thing. Suppose you are going to plot that fella. And you're going to do it by a table of values, which is very common. And we're going to pick 3 numbers. I wouldn't choose 0. I would choose 0. I'm not arguing about 0, right? I wouldn't choose 1 and 2. If you plug 1 in here, do you see that your answer is going to be 2 3/7, which we would call 17/7, but it's still. Do you really think that you're going to be accurate in plotting a point whose y coordinate is 2 3/7? I mean, it's kind of hard to judge really well where that is. Now, when you draw a line, see if you're just a little bit out, just a tiny bit out. Do you know, if it travels long enough, you could be a whole box out, you know, at the end of the piece of paper. And if your solution happens to be over at the end, do you see why you might get a y value that is 1 bigger than it should be? Because your line is just a little kink out. So the number that you use is the bottom, called the denominator. Now, what you were saying, I'm going to try and murder your poor name here. Kaliana?
Yes, Kaliana.
Kaliana, right? Kaliana was saying, look, it's easy to calculate. Let's show you what we're going for. I'm going to put the 0 in just for completeness. 0 times anything is still 0. So you add 2 and you get 2. That was the easy one. Now, if you plug in 7, do you see that 3/7 of 7 just gets you 3? 3 add 2 gets you 5. And now you've got a point that you can actually plot. Would you agree that, okay, you may have to use a kind of larger graph paper to get it in, but at least you can plot it, right? And you're not doing this, I wonder where 3/7 roughly is, right? You're not going to have that point. And if you plug in the 14(1), I believe you get 8. We go? So that would be the workaround that you need to do if you're doing really ugly equations of the form y equals. And here are some more examples. So there's, as I say, there's plenty of examples here that you can look at, probably more than you actually would choose to do. Now, one way to draw the equation of a straight line is to do a table of values, and typically 3 values of x, like 0, 1, and 2, 0, 7, and 14, things like that. A second way of doing it is to use the x and the y-intercepts. That's the place where the straight line crosses the y-axis and the place where it crosses the x-axis, as you can see here. Right? This has some advantages. One of the advantages that it has is that it's quick. Very often it's easy to do, and you can do it really quickly, and that's great when it happens. It has a disadvantage. You don't always get perfect x and y intercepts. By that I mean it doesn't always cross the y-axis a nice number like 2 or 3, or the x-axis at nice numbers. Sometimes it's going to cross at, 2.5 or something, and that can cause issues. So when you want to find the x and the y-intercepts, the places where it crosses, that means you only have 2 points. You don't have a backup point to make sure you haven't screwed up. So if you're going to do this technique, you have to be extra careful, right? Because you can make mistakes, and it happens more often than you think. So let's see if I can show you an example from scratch. So one of the advantages of the x and y intercept is that it's quick and it's efficient because of that. So let's imagine that I wanted to draw that straight line. And obviously you would probably do this in square paper, but I'm just using plain paper. To find the x-intercept, what you do is you make y equals 0, and you solve for x. Let's see what that looks like. Y is equal to 4x take away 8. Put a 0 there. Oops. Let's try it again. Put a 0 there. It's fair. Now you want to solve. How about adding 8 to both sides and then divide both sides by 4? And there is your x-intercept. Now if you want to get the y-intercept, they two things switch places. So what you do is you make x equals 0, and you solve for y. So y equals 4x take away 8. Y is equal to 4 lots of 0 take away 8. It's not really solving, it just you kind of get it for free, don't you? And so can you imagine that this point here was negative 8, 1, 2, 3, 4, 5, 6, 8, right? And then, boom, and you always label your lines. Right, as a method, it involves a little bit more algebra, but all of them involve something, right? In this case here, especially, you have to solve an equation. If you're doing the 3-point thing, it's just a matter of plugging in the values typically, right, and getting your result. Now, we normally expect equations of lines to be written in this form, right? This is called the point-slope form. It's got a name. So if you ever write an equation of a line y equals 2x plus 4, y equals 7x minus 9, right? That kind of looked at what you're doing is writing it in what's called its point slope, right? But there is another way. Sometimes you'll get and this is going to happen a lot actually, that the equation of the line is written in this really ugly format, right? So many x's plus or minus so many y's equals a number, right? This form here. And this is called, depends on the textbook, this is called the general form. It's also some textbook, it's called the standard form. So how do we plot that straight line? Because it's still a straight line. It might not look like, you know, to you, a straight line should be y equals 2x plus 1, right? But that is a straight line. Now, I could rearrange it algebraically, but I suggest you don't do that. It's a lot of work. Because all I want to do is sketch it, right? To draw it. So, let's see how it works. If I want to get the x-intercept, don't I just make y equals 0? So what's that? 2 lots of x plus 4 nothings is still nothing, is 12. That makes 2x equals 12. That makes x equals 6. So that wasn't too hard. There you go, x-intercept is 6. Now, if you take this and you want to find the y-intercept, don't you kind of switch places, right? Make x 0, right? 2 lots of 0 are 0. Add 4y equals 12. That makes 4y 12. That makes y equals 3. There's your y-intercept. There's your straight line. And we're good. So far, so good. Right, so if I gave you the equation of a line and it was written like y equals 4x minus 8, and I said, draw that line. You can pick any method you like, but would you feel comfortable you'd be able to do it, either with a table of values or by x and y intercepts? If I gave you an equation of a line looking like this, you probably want to do it with the x and y intercepts. Isn't it just kind of the natural way to go? But there's an even quicker way to do it. Do you see the x-intercept? Do you see the y-intercept? It is efficient, right? It does a good job. Now, it's not perfect. If these guys here are really ugly, sometimes you don't get nice numbers. So let's do an example of a situation where that doesn't work well. Suppose it's 2x plus 4y equals 7. Now, if I do my shortcut, won't the x-intercept be 7 divided by 2? See my shortcut? So the x-intercept is 7 over 2. And won't my y-intercept be 7 over 4? So can you imagine that you are going to have some issues being accurate? 1, 2, 3, 4. That would be the x-intercept. And 7 quarters, well, if you imagine that's 1 and you imagine that's 2, that's 1 and that's 2. There is a way that you can cope with these ugly numbers. I could probably get away with 1 box represents 1 and then just pick halfway between. I'm not so comfortable that I want to do it with 7 quarters. So here's the trick. When you're drawing your square paper, some people get caught up with 1 box represents 1 is the only scale in the universe. Do you know you can choose any darn scale you like? So if I wanted to do 7 quarters, do you know I would do 1, 2, 3, 4 boxes is 1. 1, 2, 3, 4 boxes is 2. Because won't 7 quarters be there and I won't be judging at all? If you count them, isn't that 7 little quarter boxes? Now, 3 halves, how about 1 box is a half, right? Another box is a half. 1 box is a half, the other box is a half. Isn't that a perfect place for 3/2 now. And that was a perfect place for 7/4. Do you see that now when I draw these two guys, I have a very nice, accurate drawing? The way I did my workaround was I chose vertical and horizontal scales, right? I chose my x-axis and my y-axis to accommodate the x and y intercepts, right? If the x-intercept's 2 and the y-intercept's 4, won't one box represent 1? Work totally fine. Suppose the x-intercept was 2/3, right? Suppose it was 2/3, good on, right? What do you think I should use for my horizontal scale to get 2/3? Imagine this is my x-axis. This is the origin here. What kind of scale would I use to make 2/3 an easy thing to plot? You see what I'm doing?
So you don't have to have the same scale for both the X and the Y axis?
Exactly. A lot of people think that they need to be the same. There is no mathematical reason whatsoever for that to be true. In fact, in many cases, it's a good idea that they're not the same. So can you imagine horizontally, you might do a scale of 3 boxes as 1. I do 3 boxes as 1 if the thing I'm doing is thirds, right? It's 7/3, 8/3, 2/3, right? And suppose the y-intercept was 4/5. You see, I would do 5 boxes as 1, right? That would make each little box worth 1/5. And that makes plotting weird fractions so much easier. Okay? Are we good to move on? Right. Those are the two main ways that you should draw straight lines. So we go back again. And we'll see how far we've got. So here are just lots and lots of worked examples. Of sketching straight lines. There are 2 exceptions to that rule. If you're being asked to sketch a line that is y equals a number, like y equals 3, y equals 2, y equals 4, you know, something like that. And they're dead easy to sketch. Any equation that's of the form y equals a number is just a horizontal line. And you see that this is a horizontal line where all the y values are 4. So just draw a horizontal line at 4. And if you wanted to do a line with equation x equals -3, don't you just draw a vertical line? So x equals 1 would be a vertical line at 1. X equals 3 would be a vertical line over here at 3. This one is a vertical line at x equals -3. So you don't need to do tables of values or x and y intercepts or anything. For these 2 very special cases, y equals a number and x equals a number, can't you just recognize one is a horizontal line at 4 and the other is a vertical line at x equals -3, and that's pretty much you're done. So they're easy to do, I would say. So we are going to solve system of equations now, which is the first section in chapter 3. There is only 2 sections in chapter 3, 3.1 and 3.2. 3.1 is relatively easy, I think, and relatively quick. And 3.2 is the total opposite of that. So imagine that you wanted right now just to find what can happen when 2 different lines intersect, or at least 2 lines interact with each other. If the 2 lines are totally different from each other, like this, they tend to make some kind of X shape, but they also will intersect. We call that intersect at one point. You see that? When that happens, that is what we call a consistent system of equations, right? And it has a solution that we can use. If the two lines end up being parallel to each other, do you know that they will never meet? So that means there's no solutions. So in situation one solution, and that's wherever that point where they intersect is. So if that's -1, 1, the solution is x is -1 and y is 1. So the coordinates of the place where the two lines cross is the solution to what we call system of equations. If the two lines end up being parallel to each other, would you agree that these never meet? So the answer is no solution. And last but not least, it seems unusual, but it can happen. You do the two lines and you find out that the first line is exactly the same guy and it's on top of the second line. Now, theoretically, do you know in that situation there is an infinite number of solutions? Because any point on that line will belong to both lines, because both lines are the same line. And there's some jargon terms for you: consistent, dependent, inconsistent, and so on, which you can read over in your own time. So I should see if we can do this. Right. These are worked examples and they're fine, but I find it somehow easier if you see a question from scratch than if you see the whole thing in front of you at one go. Just seems, in my mind, a little bit cleaner. So let's show you what a system of equations would look like. They would say to you, solve 2x plus 3y equals 6. Let me get another example of this. 2x take away 3y is equal to 2. Good choice. Yeah, that'll do. Yeah. Now, I'll start by calling these equations number 1 and number 2. That way it's easier if I say equation 2, you know which one I'm looking for, and I don't need to do that. And so what I'm going to have to do here is I'm going to have to draw this fella and this fella. And can you pretend just for a minute that that blue pen represents one of the lines, say line 1, and this red pen represents the second line? And they will intersect at a point, and the point that they intersect is called the solution to the system of equations. So let's go over here and look at our first problem. And I'll put next door the other one. The way these two equations are written, do you think I'm going to do a table of values, or do you think I'm going to do x-intercept, y-intercept?
Intercepts.
Yeah. Normally you only do the table of values if it's y equals 4x plus 1, y equals 2x minus 3, right? Things that are pretty much in the format y equals what's called the point slope equation, right? Now, in this case here then, I should be able to do it relatively quickly. Would you agree that the x-intercept is 3? I'm doing the cover-up trick. So the x-intercept is 3. And would you agree the y-intercept is 2? And I'm going to hold that thought. There is a temptation for me to go right over here and start doing some dots and drawing the line, right? Hold that thought just for a minute. Now, let's go over here. Would you agree the x-intercept is 1? Right? Ah, not so good. What's the y-intercept going to be?
-2/3.
Right. Would you agree that guy is going to be a bit of a problem? Right. So, before you go near plotting them, find the x and y intercept of both. That is going to be the governing factor on what would be a good scale to use on my X and Y axis? Well, I'm looking at my X's. Would you agree that X is 1 and X equals 3 are dead easy to plot? So couldn't I just do 1 box as 1? Agreed? Could I do 2 boxes as 1? Because I just feel like it. Yeah. Could I do 3 boxes as 1? Yeah, I could do any number I like. It's going to work fine. Suppose I want to plot the y-intercept 2 and -2/3 as well as here. Would you agree that I probably should change my vertical scale? Instead of 1 box represents 1? Do you think it would make better sense if I choose a scale of 3 boxes represents 1? That way, shouldn't I be able to plot -2/3? Exactly. So now back to my X axis. I know I could have done 1 box as 1. I could even do 2 boxes as 1. But I'm actually going to do, oops, even although I didn't need to, I'm still going to choose 3 boxes as 1. And there are a couple of reasons for that. One of them is cosmetic. If I did 1 box as 1, can you see I'm going to have a very squashed up graph, right? Just tiny this way and long that way. And that's visually unappealing. And it's also visually quite hard to see what the answer is. So if you have to choose a weird scale for 1, it's sometimes a good idea, if you need to, occasionally you have to change that you make both of them the same scale. There's a kind of asymmetry that makes it look pretty when you do that. Now, that's just a cosmetic thing. It's not a you'll go wrong if you don't kind of situation, but I think cosmetically it helps. So I am going to do X equals 3, which is here, and Y equals 2, which is here. And then I'm going to draw the straight line, and I'm going to call it 2x plus 3y equals 6. So far, so good. Now, x equals 1. And y equals -2/3, which I'm assuming is here, right? And then I'm going to draw the line. And that's going to be called 2x take away 3y equals 2. Can you see why I decided to actually physically do this one? Because it's not, oh, all you see in my notes is this, right? Because if you only see this, you don't get the feeling for the thought process behind how I drew it, where I plotted it, you know, the build up to that. Do you get the idea of how this is what? Now, in this case here, would you agree that there is a solution? The solution is the point where they are intersecting. Now, this point here looks to me like its x coordinate is 2. And if I go, let me figure out what this is going to be. And that its y coordinate is 2/3. I am working with a problem that you won't be working with. I am working with plain paper. Do you know if you do square paper, it's much easier to figure out where something is. So I'm kind of horizontally trying to judge where that is. But the answer to this question, the solution, is that guy. Now here is something that's going to be weird. You will get a question like that in the homework, and all you will be doing is, in a box, writing that. So most of what you do doesn't appear on the computer, right? You don't type in this, you don't necessarily even draw this. that gets done as like working at your side. So you may want to hold on to your working, because, you know, staple it together or something, so that when you go back and you look at some of the questions, you can say, okay, I'm revising for the final. What did I do? Yeah, I see that. I see that. You can kind of see what you've done. If you just go back and look at the homework questions, do you know all you will see is solve this, that's your answer. And you're going to look at that answer and say, how the heck did I get that? So I'm just telling you that it's a good idea, in my opinion anyway, it's a good idea to hold on to your working. That's basically going to be your notes when you want to revise and get ready for the test. The homework questions themselves, you just write down the answers in boxes. You don't really get to do much more than that. Now, if you weren't aware, oh, maybe I should ask it this way. How many shots do you get in the homework? Does anyone know?
3.
You get 3. So if you type it in the first time and it doesn't work, at least it'll tell you you're wrong. You can go back and say, oh, darn it. It wasn't negative 2/3, it was positive 2/3. Because one of the things you might do is get your sign wrong, right? Other things you have to be careful about. It's kind of hit and miss. Sometimes it doesn't matter, sometimes it does. Can you imagine that the question was 2,3/2, right? Imagine it was that. That's the answer they'd expect, and they will always accept that answer. But sometimes you forget, and you call it 2,1/2. Isn't 3/2 1/2? So you're right. But it will go, you're wrong. And sometimes you'll type in that. And isn't that also the same thing? So what I'm just saying is, it's not consistent. Some people have told me in the past, I typed in this and it worked. But then the next question, I typed in a similar question and now it's not working. So it's not even consistent. It might well take all 3 answers for question 4. But then in question 5, it wanted a fraction. And even although you typed in the right numbers, it wasn't in the format that it wants. So what's going to happen here is, if you'd use up your 3 shots and then it tells you the answer and then you look at it and say, but that's what I said. But you've lost a homework point because it says it's wrong. Shoot me an email saying, look, this is what I typed. I'll have a check on it and I'll just grade you accordingly, right? Because you really shouldn't be dinged for that. But will we work on the principle, and that way we'll never need to worry about it because it always accepts this, that the X and the Y coordinate should always be written in fractional form, not decimal, and that they should be written in what's called improper form, right? 3/2, 7/4, not as a mixed fraction like 1/2. And if you stick to that rule, you'll never use the other 2. And so you'll never need to worry about losing the odd point here and there because the computer doesn't understand you. Are we cool? So that's our first example. That is an example of a system of equations with one solution. Let me show you, I'm going to do 3 examples altogether. Let me show you the second one where something different happens. So we're going to have 3x plus 2y equals 10. I want 10. I want a number that works well with them. Equals 12. There, that works well. Let me redo that. 3x add 2y equals 12. Okay, that's our first equation, our first straight line. And for my second one, I'm going to go 6x plus 4y equals what works well with them. Let's do 36. So we're going to attempt to solve this system of equations. Again, in this situation, would you agree that probably the X and Y intercept would be the best way to do it? When equations are written in their general format, that's typically the better way to do it. I've deliberately, I hope anyway, deliberately chosen these to be quick. Right, so let's see what we get. Get that out of the way because it's distracting me. X-intercept 4, Y-intercept 6. So X-intercept 4. I've just broken my own rule. Shouldn't you make sure you do both before you do your scale? But I happen to know they're all whole numbers, so I get away with that. Right, cover this guy up. X-intercept 6, Y-intercept 9. Now you join these two together, you get 3x plus 2y equals 12. If you join these two together, you get 6x plus 4y equals 36. And this, I can guarantee, is going to happen in some of your questions. Let me phrase the question this way. Is there a solution to this system of equations?
No.
No. So that's your answer. No solution. Right. So you'll have your box down here. And no solution. So you can imagine that happening, right? Sometimes. Now, how about this is the third situation? I said I was going to do 3, so we've done the two things cross and there's one solution, right? We've done the 2 parallel lines, no solution. What's the third one going to be?
Infinite solution.
Infinite solutions, right? Infinite solutions happen when both equations end up being the same straight line, right? So imagine that I gave you the equation. Oh, let's do it this way for a change, a little mix and match. Y equals 2x plus 4. That's one of them. And 2y take away 4x equals 8. We'll make that the second equation, right? Now, I'm as always, I want to sketch these equations, and then from there I can get my solution. Okay, I'm going to do this one here. I'm going to break my own rules again. I actually know that these are nice numbers, so I'm not going to wait until I solve both before I decide what scale. They're both going to be nice numbers. So if you look at this one, 2y minus 4x equals 8. My x is a little bit short. The x-intercept would be -2. And if I cover this up, won't the y be 4? So that is our first line. And that's the line 2y take away 4x equals 8. Okay, now let's look at this fella. I'm going to sketch him. And, you know, we'll see what happens when I sketch them. You kind of know what's going to happen, but let's pretend we didn't. Can I use a table of values on this? Could I do an x and y intercept on this? Yes. Does it matter which? No. Which way do you want me to do this? Do you want me to do this as an x-y intercept question, or do you want me to do this as just a table of values type question? You tell me and I'll do it that way just to show you.
Table of values?
I know, I haven't done many of those, right? So if I do a table of values, In this particular case here, I think 0, 1, and 2 work really fine. Right. Would you agree that's a pretty easy equation? You're not going to get anything weird out of it. The y value then is 2x's plus 4. So 2 nothings plus 4, that guy there, and 2, 4, 8, that guy there. So let's see what I get here. At 0, it's 4. Oh, it's that point there. At 1, it's 6. Can you trust me that 1, 6 ends up being there? And at 2, it's 8. Can you trust me that that guy there ends up being 8? Can you see that the 3 points that I got from my table are also on that line? What does that mean then? Doesn't it mean that these two lines are actually on top of each other? They're really the same line. They algebraically might not look like they're the same thing, but really they are. And when you get one guy on top of the other, then the answer or something like that. Maybe the word's just infinite. Maybe they only need you to say that. Do we feel comfortable about the general process then of how you use sketching these fellas, right? And if they cross, you get a solution that you write down, x equals this number, y equals that number. If they're parallel, you say no solution. And if they end up being one on top of the other, you just say infinite solutions. We're comfortable with that, right? So what I'm going to do is I'm going to give you 3 questions to try. And we'll let you just work on it on your own, and I'll give you, say, 15 minutes, 5 minutes each. And then we'll come back and we'll check that that we agree. If that happens, then I'll feel comfortable about moving on, right? So for most of you. So I'm going to give you 3. You can kind of tell what's going to happen. Since I'm going to give you 3, you can kind of tell that isn't one of them going to probably have an intersection, one of them is going to be parallel, and one's going to be identical. What you don't know yet is which one is which, right? So I'm going to at least add a little bit of suspense to which question. So if you give me a few moments just to kind of set them up, I'll put them in boxes, that way I can think about what I'm going to put in here. And I'll try and mix and match them a little bit so that sometimes it's table of values and sometimes it's x and y intercept. Hopefully you've got square paper. If you don't, do your best, right? You'll know if you're kind of in the right place. I get lots of paper very cheaply out of pound stretchers, pound something. That's the British name for it. Dollar Tree. Dollar Tree. Go there, grab a whole load of square paper, right? If you've got plenty of ink on your printer, do you know you can go online and just get a square paper template and print 100 pages or 20 pages, whatever you think you need. And that's how you can get square paper if you don't want to do that. Okay, so the first one's going to be y equals 2x plus 4. 3y take away 6x equals 18. So that's going to be your first one. 2x plus 3y equals 12. X minus y. I gotta make this work here. Yep, that's my second situation. And my third situation. Okay, guys, you now have 15 minutes and good luck. Hopefully you followed the same kind of rules. If we take them one at a time, let's look at this one first then. Table of values, maybe to do that one, but you could have done it the other way if you chose to. Let's see what we would get. In this case, the y-intercept would be, what, 4. The x-intercept, I believe, is, what, -2. That's on the first one. So I'd get a line, look something like that. That look about right? Yeah. Okay, so that is this one. If you cover this guy up, the x-intercept is, what, -3, which is here. And the y-intercept, which is 6, which is up here. So, even bad, no, it's very badly drawn by me, but can you pretend that I can draw better than that? That one had no solutions, right? It was parallel lines. If you drew it better than I did, you would see it was definitely parallel, but you know, I screwed up. Right, if we do this one here then, I can do the shortcut on this one. The x-intercept will be 6. The y-intercept will be 4. So I'm looking for a line, something like that. We check on that. Y-intercept 4, x-intercept 6. I know my scale looks a bit out, but that's fine. And this one here, x-intercept is 1. Y-intercept is what, -1. So I'm looking for, oh, I should have paid more attention to this one. This one, the two guys cross, agreed? I believe they cross at 3,2. Right, so if I'd drawn that well on square paper, you would have seen that. And this last one here, if you look at this guy, it's got a y-intercept of 5, and it's got a rather awkward x-intercept roughly here, and it goes that way. And if you do this one, it ends up being the same guy. So in that third situation, you get an infinite number of solutions. In this situation here, x equals 3 and y equals 2. Now, there's quite a few times in the homework where they ask you to reuse up words like the equations are dependent, the equations are independent, you know, terminology like that. If the two lines cross as they do here, they're independent, right? And if they don't, they're dependent. So I'm not going to spend a lot of time on that. It's something you can read up on and check in your own time. So what I'm going to do now is just go back and we'll have a look at the homework, if I can find it where the heck I put it, and see, that's your files getting downloaded there. Where are you? Darn space. I'll do this one. Here we go. Right. Are you looking at Cengage right now, or will I have to go out and in? I nod, so I'm assuming that's Cengage. So if I hit the view button, we should be able to go back in and see some of these questions. Here we go. And this thing here has the solutions set up, so I'm going to have to kill that or it would distract us. And we'll go back in a second time. I don't think you can see this. Can you see the questions? No, I didn't think so. So I'll be with you in a second. I just do that, go out and go back in thing. It's a pain in the hysteria that you have to do that. Right, you're now looking at the questions. Right. So, question 1, fill in the blank. Here are two, these are called a system of linear equations. See how easy some of your homework questions are going to be. Right, so don't overthink them when they're easy like that. Now, here is a picture of two lines. And it gives you some choices here. And there's no solution, right? So it's one of these two. And it's either independent or dependent. And I'm going to let you read that over yourself, because if I just tell you, you'll nod and do it yourself. Now, in this one here, it's kind of sneaky. Use this picture, these graphs, And it's being used to solve this fella. Negative 3x add 9 equals x add 1. So that's a bit weird. Which one of these three, the red, pink, purple, whatever you want to call it, the purple, the blue, or the green, which one of them is y equals? Imagine there's a y next to that. Which one of these three is y equals negative 3x plus 9? Y equals negative 3x plus 9. Now, you got to think a little bit here because it's not perfectly obvious, but they are there. Where's the x-intercept for y equals negative 3x add 9? Where does it cross the x-axis? So pretend this bit here
3.
is exactly right. Pretend this x plus 1 isn't there. Imagine that said y equals. It would be at 3, right? You know, there you go. That makes it the blue line. Which one of the two that are left is y equals x plus 1 now?
Purple.
I agree. Do you want to explain to the others why? Because they may be looking at that and saying, oh, how did you know that? What did you do in your head?
I was looking at the y-intercept
Which is 1.
at 1.
And there's only one of them that's true. So, you know, if you get in a situation like this, because question 6 is very similar, you might want to look at x-intercepts or y-intercepts, because typically one or the other is going to be unique, and that'll tell you which colour it is. So back to this question. We now know that this line and that line, so that means we're meeting here, right? Now, when you meet here, do you see that the x-coordinate is 2? That's what they want you to take. So if you were wondering what the heck that question was about, because to be honest, I think it's a bit vague. It could have been a lot clearer, right? That's what they're asking. Figure out who the two lines are. There's your intersection, and write down what the x-coordinate of that would be. I think that question would have been much better if they'd given you the x and the y, because that might have made you think a little bit more about what the heck it was going on. But it is what it is. Question 6 is a rerun of the same one, right? Same kind of question. Are we good? Okay. Now, here's something I haven't done, and I guess I really should, because there's a couple of examples of them here. I think there's 3 of them. Questions 8, 9, and 10. They give you a coordinate of a point, 2, negative 2, and they say determine whether the ordered pair is a solution of the given system of equations. So is 2, negative 2 going to work for this fella, and is it going to work for this fella? If it works for both, you'll say yes. If it only works for one of them, or it doesn't work for any of them, then you will say no. Now, what I mean by working for them, I mean that if you plug x equals 2 and you replace the y with negative 2, these two things equal each other. So let's see what happens. If x is 2, won't a half x be 1? If y is negative 2, is negative 2 add 3 also 1? Right. I think I'm probably doing too much verbal. I think I need to show you. Sometimes you just need to see something rather than hear it. So I'll do my own version of that same thing, right? So imagine you had 2 equations. One of them is called y equals 2x plus 3, and the other is called, oh God, I gotta make sure this works first. Right. And we're being asked to check that one, right? So the question had a little, a circle with a yes on it, right? And a circle with a no, that was it. You didn't have much of a choice. So let's see how this works. X is 2 and y is 7. Let's find out if it works. Start with the first equation. If I replace the y with 7 and the x with 2, are both sides equal to each other? Yeah, so it works for the first one. Now, if I write down the second equation, which is this one, and I place the x with 2 again, and the y with 7, are they both equal? Yes, they are. That means that this solves the system of equations, and you will do yes. See how that works? That makes sense now. Now, if they'd made this 14, right? When I got down to here, do you see I'd have 11 equals 14, which it's not, right? 11 is not equal to 14. Then wouldn't I go and I'd say, no. If the first one fails, right? If the first one doesn't work, do I even need to check the second one? See, if the second one works and the first one fails, doesn't it still fail? The answer's still going to be no. So if you do one of these, there's 3 of them. If you do one of these questions and the first one, right, this one doesn't work with the top equation, the answer's no, and just move on. Since you get 3 guesses, do not do this because it's bad math and it's not going to help you when you have a test. I'll say yes, and if it tells me I'm wrong, I'll say no. If you've got 3 guesses, you've still got 1 in the back, right? You're going to get the right answer, but you're going to get it just because you're being lazy, right? So why is that important? Well, imagine you get this question in the test. You don't get 3 shots. You get 1 shot. So you got to know how to do it, right? Otherwise, I guess you'll be doing a 50-50 guess when the test comes, and that's not a good average. And secondly, I don't see you're working for homework. In homework, you just type numbers and things into boxes, and that's fine. That's you're working. You are doing for your own benefit, and you're going to hopefully keep it for revision. But when we do our midterm, you will actually do working, and you will send that working to me. And if I see working, I can give you partial credit if you're half right. You know, you did the question correct, but you kind of did this bit right and you screwed up on the second one. At least I can give you half the points instead of a big 0 out of 10. You can get 5 out of 10. So there's benefits there. It's also to stop cheating. If I don't see working for a question that clearly needs working, I'm going to assume that you found the answer some nefarious way that you shouldn't have, and I'm just not going to give you the points for it. Now, that's for the midterm and for the final. But when we get closer to that, we will do that. Are we comfortable now about the process of how do you check if a point is a solution to an equation and what you do? So I'm going to do my usual zoom in and zoom out and all that, carry on. You know, one day they'll figure a way of doing this just to reduce the number of times I need to do this in and out thing. So that's going to get you through questions 8, 9, and 10. Okay. Now, question 11. Solve that system equation or solve this system by graphing. That is them saying, on your own time, draw the 2 graphs. If they cross, which I'm sure they do because the way it's phrased, they cross. I'm not saying this is the right answer because I know it's not. But if you think it's 5, 1, do you see that's how you would write it down? Simple as that. So you see that you don't write any working in these homework things. All they do is they say right at the end. If you get it wrong, of course, it will say, you know, you're wrong, try again, things like that. But we only get 3 shots. Now, in question 12, it's a little bit different. I kind of like these versions where they give you some graphs. You're still going to solve x add y is 6 and x take away y is 4, right? So you're going to draw those 2 guys. And once you've drawn them, you're going to look at these pictures. And one of these pictures is going to be your picture. And whichever one it is, you're going to put the check mark on it. So do you see that's their way of kind of forcing you to do a graph? Because you've got to draw a picture to know which picture it is, right? I could do a guesstimate of this one. Could be that line. Let's see about the other choices. 4, K51. Yeah, that's interesting. Actually, I think it's this one. Here's another little thing. WebAssign's quite clever. Do you see when you see red, or at least I see red, I don't know if you do, I get a special version of the program. You see these numbers that are red in 6 and 4? If you do this question and John, who lives next door to you, does the same question, do you know he won't get the same two numbers? He'll get 8 and -3. So it means that you do kind of unique versions of the same question. So you can't really phone up John and say, what was your answer? Because yours might be that top one, but his might be that bottom one, right? So you need to know how to do it again for obvious reasons. Question 13, 14, 15, keep going, 16, 17, 18, 18. 18 shouldn't be there. I'm certain I deleted 18. Okay, don't worry about 18, it's not there. It says use a graphing calculator. We're not going to get you to do that. It would take you too long to do it, and I don't want you to learn how to do it in a graphing calculator, because then people cheat and use it for all the questions, and it stops you doing the algebra. So forget about 18, it ain't going to happen. There is a cool question that I haven't done, and I'm glad I looked at this, and that's question 19. And that's one of my dogs. I'm saying hi. Sounds like, yes, it is, it's Maggie. She's the princess of the family. Now, I'm going to show you how to do question 19. I'm just writing it down right now so I can use the same values that it has. I'm not going to finish it, I'm just going to start it off for you. Okay, so hold that thought. 19 we're going to do, but let's just finish off the rest of these and then I'll finish with that question. Question 20 and 20. 20 is back to the usual. Can you imagine drawing these two lines and getting a solution, typing it in? This one here is a baby question. Do not overthink this one. Y equals 5 meets up with x equals 3. Y equals 5, horizontal line. X equals 3, vertical line. Where do they meet? They meet at 3, 5. Do you know, I didn't even need to draw that one. I could, I guess. Sometimes you get an easy question in amongst all the hard stuff, right? Would you agree 22 is a visual version of that same situation? And I'm not going to tell you the answer, you can figure that out. Question 23 is awkward but doable. Question 24 is certainly awkward and doable. Question 25 I'm actually going to take a note of because it's a similar problem to 19. And I'm going to show you how you can fix that. Question 26 is pretty awkward but doable. And then they do a couple of how to use this little gizmo here to draw straight lines. So you plot a dot, and then straight line through it. And that's something you have to physically learn how to do. Okay, I am about to go and show you some of the bits and pieces that I didn't cover. So here they are. Question 19, question 25. Question 19, question 25. I better redo 19, I need more room. We're being asked to solve this system of equations. I could just leave all these ugly fractions and fight my way through and find an x and a y intercept. I mean, I could do that. I would suspect that it would be messy and very easy to make a mistake. So what I'm going to do instead is a clever little algebra trick. I call this is my made up What is it? What do you want? What's up? Come on, let's go. She just wants attention. Right, here's the trick. I call it as long as you do it to both sides, it's okay rule, which is a very long name. And what I'm going to do is I'm going to multiply everybody by 2. So this equation becomes 2y equals negative 5x plus 1. And I'm going to look at this equation. I'm going to multiply everybody by 2. And now it becomes 4x take away 3y equals 10. Now, although the question isn't that much easier, would you agree that these numbers are just easier to deal with if you want to find the x and y intercepts? Because the fractions are pretty much gone. Now, it does mean that you're going to have to do one of those awkward ones. Can you imagine? You might have to do 5 boxes on the x-axis, right? 5 boxes is 1, 5 boxes is 2. And you might have to do something similar, or maybe intense going in the y-axis, but eventually you'll get that to work. So that's how you get around this one. This question here has got y equals negative 3, which I kind of like. By the way, that's a horizontal line. This fella here I do not like. What do you think I'm going to multiply everybody by just to make it an easier algebraic situation to deal with? What do you think I'm going to do here?
Multiply by 3.
Yeah. So it's going to become 3y equals 2x take away 7. Now, if I write the other equation down, we're now looking at that situation there. Now, I think these are just easier to deal with. You know, when you deal with fractions, don't you tend, I tend to anyway, don't you tend to make mistakes? You know, fractions are just messy and sometimes you forget to, you know, add, divide, whatever you're trying to do and you do the wrong thing. Now, if you do it in this way, can you see that you can simply just replace that by 3 times the y value, which is negative 3, is 2x take away 7. That makes negative 9 equals 2x take away 7. If you add 7 to both sides and then divide, you now have your solution. X is negative 1 and y was negative 3. Right? Came out quite nicely. Okay. Well, that is us finished. How to solve system of equations graphically. We're now moving on to section 3.2. And we're going to look at how to solve system of equations using algebra. That means no more drawing straight lines. We're going to get the x equals 4 and the y equals 2, whatever the solution might be, if there is a solution. We're going to get that by doing algebra, right? Solving equations, essentially. Right? There are 2 distinct techniques. The first one we're going to look at is called the substitution method. And pretty much everybody, every textbook I know calls it that. And the second is called the elimination method. It's also called the addition method. It's got 2 names. Actually, the addition method is more common. Although the textbook, I think this textbook calls it the elimination method, right? But it's just a different name for doing the same thing, right? So let's focus on the first one, what's called the substitution method. Now, there's a lot of advantages to doing it algebraically. One of the big disadvantages of doing it graphically is that as long as the 2 lines intersect at nice numbers, right? 3,4, 5,7, right? As long as they do that at nice numbers, it works fine. But it's not really very good if the numbers are really weird and, 17/33 or something, right? You wouldn't really be able to read that off from a diagram. Algebra doesn't care how ugly the answer is. The algebra will still tell you the answer, as weird as the fractions might or might not end up being. So that's one of the big differences. So let me show you how the substitution method works. Suppose you had y equals 2x plus 1, and you had 2x plus 3y. Let me pick a number that works here. Is 11. Now I could draw these, I could find out where they intersect, and by the way, they do intersect, so there's one solution. And I don't know, it takes a fair amount of time, doesn't it, if you draw and you're being accurate about it. This is how substitution works. In this particular question, what you're telling me here is that y is the same thing, it's worth the same as 2x plus 1. That means that this y here can be replaced, another word for replaced is substituted, can be substituted by that guy. So what has happened is that you see equation 2, the y in equation 2 is replaced by 2x plus 1, substituted by it. Now, all I'm going to do for the next few lines is good old-fashioned solve equations, right? The usual things that you end up doing. So, would you agree the first thing would be to distribute the 3? So 3 lots of 2 get me 6x, and 3 lots of 1 get me 3, and we're looking at that. Okay, talk me through, what would the next step look like? What would you do next here? Not meant to be a trick question.
Combine like terms.
Okay, so combine the x's. Someone else said that, I agree. We're now going to do my as long as you do it to both sides it's okay rule. So I am going to subtract 3 from both sides. I'm going to divide both sides by 8, and I have half of the solution. I now know that x equals 1. Right, that's the x coordinate of the solution is 1. So how do you think I'm going to get the second half? The y part of the solution.
Plug the x in.
Yeah. I can plug it into equation 1, which is what I'm going to do. I could plug it into equation 2 and it would work. Why do you think I'm not going to do 2?
It would make
horrible, right? It's more work than I need, right? I don't want to do it if I don't need to. Always take the easiest road if you can. So I'm going to take this fella here, and I'm going to, I guess I should put up here for my notes, put x equals 1 in. I like the word put because it's shorter than saying substitute, although it's the same word, right? It does the same meaning. So what are we getting? Y is 2 lots of 1, add 1. Y is 3. And so your solution will probably look like that in a box in the homework. Because the homework doesn't ask you to do anything except the answer. You'll probably end up writing it like that. You see x is 1, y is 3, you're done. Agreed? Shouldn't I be able to check that that actually is the correct answer, right? Let me show you. I don't do checks a lot because they take too much time. But let's go for it. Y equals 2x plus 1. And I'm going to check that 1, 3 works. Well, that means x is 1 and y is 3. So y gets replaced by 3, x gets replaced by 1. Check. Then I can go to the second equation, right? 2x plus 3y equals 11. Well, 2 lots of 1 plus 3 lots of 3. 2 add 9, 11. Check. See, it works. Kind of cool. Now, in a normal everyday homework situation, won't you just plug that in and it'll tell you you're right? But can you imagine in a test situation where you want to just be 100% sure? It wouldn't be too difficult to do this with it, you know, just to be doubly sure that you solved it. Now, there is a problem, and it's not a problem with the substitution method, it's just a general problem. One of the situations is one solution. And visually, one solution means that guy meets up with that guy, right? But isn't there two other situations? Parallel lines, no solution. And then the same line, infinite solutions, right? Pens down. What does the algebra look like when this and this happens? This is what the algebra looks like when there's one solution, right? You solve, you get an x value, you use that, you get the y value, you're done, right? That's what the majority of questions are probably going to look like, right? There's going to be one solution and you'll find it. But let's show you what happens if you get a system of equations that have no solutions, and what does the algebra look like? So that when this happens, you can say, ah, that's because they're parallel and there's no solutions, right? So here's an example of me doing that kind of question. So let me see if I can make one off the top of my head. Oh, y equals 3x take away 2. So what's that going to be? That's, right. And then I'm going to do 2y minus 6x equals 10, right? So imagine your system of equations was solve this. Okay. Now, this fella here is very important, because isn't this going to be the guy that I'm going to use to substitute the y in the second equation? So I know that y is 3x take away 2. That means this can be 2 lots of 3x take away 2, subtract 6x, then equals 10. If you distribute, you get 6x take away 4, take away 6x equals 10. If you combine the like terms, you combine the like terms and the x's disappear on you, right? 6x, negative 6x, gone. And worse than that, look what's left behind. Negative 4 equals 10. And your first reaction is, I've screwed up. Because negative 4 isn't 10. What have I done wrong? Nothing. That's exactly what you should get. That is what two parallel lines give you. What that is saying is negative 4 is never going to equal 10. Why is it never going to equal 10? Because the two lines are never going to be equal to each other, right? They're never going to meet. Now, it doesn't need to be these two numbers. It can be anything. It could be 7 equals 4, 0 equals 22. You're just going to have all the variables disappear on you, right? And you're going to be left with one number that's 8 equals a totally different number equals 7. So if you ever see that, you will then, in your little box, say no solution. Why? Because that's what happens when you have parallel lines. If you use the substitution method on two parallel lines, this is what the algebra does, right? The x's disappear on you, or whatever the variable is, and you're just left with numbers. Right, there's a third possibility. Couldn't there be an infinite number of solutions because both lines are the same? Right, that could happen. Let's see what the substitution method looks like when that third situation appears. So this is what essentially parallel lines do. How about, oh, let's be different. X equals 4y minus 1. There's no reason in the world why it should always be x equals, right? Sometimes y equals is better, right? Or vice versa. Let's go 3x, take away 12y equals -3. Okay, so there's my two equations, and I'm going to solve them. In this particular case, do you see I'm now going to do x equals rather than y equals? So 3x becomes 3 lots of 4y take away 1. Subtract 12y equals -3. Distribute 12y take away 3, take away 12y equals -3. Uh-oh, the y's disappear now. And I'm left with -3 equals -3. Now you're thinking, what does that mean? That means you've got the same line on top of itself. That means infinite solutions. And the way we interpret that is, isn't -3 equal to -3 forever? So the line has an infinite number of solutions. Pick anything you like as long as it's on the line and it's going to work. -4 is never equal to 10. There's never going to be a solution. That's parallel lines, no solution. Most of the time, it's going to look like this fella here. Right? Are we cool with this method? Are we getting a little bit of grasp of how you do this method called substitution? Right? Now, there's still more to it to come. It's not that I'm going to change the method. It's just going to make it, you have to do it with more awkward situations. So let me show you an example of a more awkward version of that same method. We need to do the substitution method. Don't we need an equation that's y equals or x equals so we can stick it into the other equation? And in the ones I gave you, they were really nice to you. They gave you one ready to use, right? Y equals 2x plus 1, ready to use. Y equals 3x minus 2, ready to use. X equals 4y minus 1, again, ready to use. So what we need to do here is we need to decide which one of these two equations I'm going to pick that I can rearrange to give you a y equals or an x equals. And it doesn't really matter which equation you pick, 1 or 2. It doesn't really matter whether you decide to rearrange it to become x equals or y equals. All combinations work with this one caveat. Don't you want to pick the one that's the least amount of work? So as I look through these two equations, do you think I'm going to pick equation 1 or equation 2 just by looking at the kind of numbers that are in there? Yeah. Agreed? 1. Now, I've got 2x and I get 4y. I guess it's a toss-up here. Me personally, I'd probably do the x equals. You might decide to do the y equals. Totally fine. We're both going to end up with the same answer. So it's not a problem. Right? So, I'm going to take this fella and I'm going to rearrange him to become x equals. And I'm going to use my tried and trusty, as long as you do it to both sides, it's okay method. So what do you think I'm going to do to both sides to try and get x on its own? I know you're saying it because I can see your mouth moving.
Subtract the 4y.
Would you agree? Subtract 4y from both sides? So far, so good? Now, Would you agree that the last step in this question is to divide both sides by 2? And when you divide both sides by 2, I get that. Now, if you don't need to do this, I'm just doing it because I feel it's necessary. I'm going to write underneath this guy, equation 2. So there's the one I'm going to use to substitute. I'm going to substitute it into this equation, right? The second one. So what am I going to get? I'm going to get 3 lots of 4 take away 2y, subtract 2y equals 5. Now, one of the cool things about the substitution method is it doesn't care how ugly the answer is, you will get the exact value. So let's see where this one takes us. Distribute. Combine the like terms. Okay, where are we going next?
Subtract 12.
So I'm going to end up with this guy, right? Would you agree the next step is divide both sides by -8? Now, if you divide both sides by -8, I guess it might start life off as that, but doesn't it finish at 7/8? Now, do you see how ugly that answer is? But the algebra didn't care it was ugly, right? You still got it. Can you imagine that might be quite difficult to read off a graph? Now, I'm only halfway there. I know the y solution. Don't I still have to find what the x part of the answer solution is? And it shouldn't be a surprise, aren't I going to use this guy to do it? So I'm going to take x equals 4 take away 2y. That's going to be 4 take away 2 lots of 7/8. That's going to be 4 take away, I don't know, what, 14/8? Okay, you're going to have to deal with fractions sometime in your life. So 4, do you get? You get 8, 32. 32/8 take away 14/8. That's going to be 18/8. And that's going to be 9/4. Okay, we got it. So your solution is going to be 9/4, 7/8. I deliberately gave you a really ugly one. The vast majority of questions are not going to come out that badly, right? But you know, if you can do a difficult one, can't you do an easy one a lot better, right? So if you say, okay, that was horrible, well, think about that's probably as horrible as they're going to get, right? Most of them are going to come up with much nicer numbers. Are we cool with that? Right. So if you solve a system of equations using the elimination method, you have to decide if the two equations are like this, you have to decide which equation you're going to use to convert into x equals or y equals. So let's do some practice at picking equations and turning them into x equals or y equals. I'm not going to do the whole question, just the beginning part of the process. So imagine we had a system of equations like this. If I'm going to use the elimination method on this question, which one do you think I should use to turn into x equals and y equals? The first equation or number 2? Which one do you think would be the easiest to convert into an x equals or a y equals?
1.
1. You agree?
Yeah.
Which one of those two, now that you've decided to choose one, y equals or x equals, which do you think is going to be the least amount of work?
Y equals.
Agreed, Mark was mouthing y. Is that what you were mouthing? I think I said y anyway, right? Okay. So how about, there you go, right? And then off you go and you do the process. Try another one. How about 4x plus 3y equals 8? and x plus y equals 10. Who do you think? One or two? Should be easy.
Two.
Agreed? Just need somebody to say it for the rest of us, right? Two. Oh, here's a choice, X or Y?
X.
Why? That's the question, why? Question mark. Because you felt like it, right?
Yep.
Would you agree Y equals would be equally easy? You can imagine that two people doing the same question could actually choose a different X equals or a different Y equals. But you know it doesn't matter because the final answer is the same solution. So you look at a question and you sometimes you might choose a bad equation. And all I mean by that is one that involves you doing a lot more work than perhaps you needed to. But as long as you follow the process through, you will still get the solution. So at the end of the day, there's no real damage done, right? You'll still get the answer right. You'll still get the points. You'll still move on. When I look at equations, I think most people tend to do it this way, is that if either one of these terms has a 1 in it, isn't that a good candidate for the guy you're going to use? So if it's 15y plus x, I'm probably going to use the x guy, right? If all of them have numbers, you know, if it's like 3 of this and 2 of that and all this carry on, you know, see if it's something really ugly like this, you could probably randomly pick anything you like, because I bet you all of them are equally ugly to fix. And you probably just say, to heck with it, I'm going to use that one and do it as x's, right? Or I'm going to pick this one and do it as x's, or whatever it might be. Most of the time, the questions are designed in such a way that they come out quite nicely. Here's a different situation. We haven't encountered this particular extra problem. Here's a piece of advice to you. Never leave an equation with a fraction in it. My experience is that we screw up when there's fractions involved. We just don't handle them well, right? So what do you know what I normally do with the question? If I see a fraction, I don't even care what the question is normally. I figure a way of making that fraction go away. And I use the trick that as long as you do it to both sides, it's okay rule. Now, this is the culprit. I really don't want to keep halves and thirds, you know, because when I start doing substitutions and have fractions inside other fractions, you know, it's very easy to lose it, right? So what could I multiply both sides by to get rid of halves and thirds?
6.
6. Now, if you multiply everybody by 6, this becomes 3x, this becomes 2y, and this becomes 36. And this guy, I'm not going to do anything to because I kind of like how he looks. So do you see that the original question has now been turned into a much more user-friendly question? Agreed? Just to finish this one off, equation 1 or equation 2, which one do you think you're going to go for? What about you,
1.
McKenna? Oh, I've heard 1, but come on, McKenna, do you want to go 1 as well? Are you just a follower? Okay, since you're going to say 1, you get a backup question. Nothing wrong with 1, I kind of like it myself. X or Y? Are you going to make it an X equals or a Y equals, McKenna? Which one do you feel would be less work?
X.
Interesting. I'd pick Y. McKenna's not wrong. X is actually quite nice as well. It works pretty well. I'll just take you through the steps to show you what McKenna would have done then. So the first thing you do is subtract 2y from both sides. And then you divide both sides. Oh, I take it back. I take it back. it's not that that's wrong. I just don't like 2/3. Right? Now, you can do that and go through the process. Trust me, it'll be fine. You won't get it wrong, right? You'll get the right answer. I'm going to go Y. And see if that's any better. Well, if you subtract 3x from both sides, you get that. And then if you divide by 2, oh, darn it. We're both equally screwed, right? You're not going to get out of that. There are some questions with the best will in the world, you're just not going to get perfect numbers, right? And you're just going to live with that. So I would be substituting this guy or this guy into the second equation. And we would hope that the rest would come out reasonably nice. We call with the process of how you get rid of fractions, because that might happen. Here's another kind of related version. I don't like fractions. I'm not really that keen on decimals. They're a little bit easier to deal with because calculators do most of the work for me, but I still don't like them. So I tend to eliminate them as well. What do you think I would multiply everybody by in equation 1 just to make the fractions disappear? Yeah, exactly, 10. So 3x, 2y equals 17. We'll call that equation 1. And 2x add y equals 22, and I'll call this equation 2. And this time, I don't think there's any argument, or at least I don't think there should be. Would you agree I'm going to use equation 2, and I'm going to make it a y equals? And off you go, and you get that done. Are we comfortable about this process then called substitution, right? You're going to be given 2 equations and you deal with them, you know, the best ways that you can, right? Now, I think we need a joke, right? You agree? Has some of you, I know, Manny, you've heard my joke, haven't you? You want to tell everybody how bad they are, or are you just going to let them find out in a few moments?
They're great.
Okay, she likes them. Good. Right. So I can't remember which one. Did I tell you the one about the husband and wife in the aircraft?
Yeah.
Okay. So let's tell you a different one. Scotsman, Englishman, and an American die and they go to heaven. And they're looking around heaven and it's really pretty and beautiful and they love it. And the Scotsman especially is dead excited. He's all, oh, this is great, this is brilliant. But it's huge, heaven's really big. And so he says to St. Peter, the Scots guy says, you know, heaven's really big. Do we get a car so we can get around? Do you get a car in heaven? And St. Peter says, yes, of course you get some kind of transport. You can get a car if you like. And the Scots guy says, can I get any car I want? I want a really fancy car. Can I get any car I like? And he says, well, it doesn't quite work that way. It depends on your answer to a question, what kind of car we give you. So the three of them says, okay, what's the question? So he goes to the Scots guy, St. Peter, and he says to the Scots guy, how many times were you unfaithful to your wife? And he said, I was never unfaithful to my wife. And he says, looks at his little book because he has all that, and says, you're right. Scotsman says, great. He says, what kind of car do I get? He says, get top of the line. You're getting a big fancy Ferrari sports car, open top, convertible, big engine, red, all the bells and whistles. And he jumps in it and boom, he's off. So they go to the Englishman and they say to the Englishman, same question, says, how many times were you unfaithful to your wife? And he said, just once, and she forgave me. That was it. Never done it again, just once. And it looks at his book and said, that's true. And the Englishman says, well, what kind of car am I getting? He says, well, I'm not going to give you the same kind of car as the Scotsman. You're just going to get a normal Ford, right? Four-door, whatever it is, Ford Escort, right? And he gets in and he drives away. And they go to the American and they say, okay, how many times have you been unfaithful? And the American kind of fidgets around and gets kind of embarrassed. And St. Peter says, look, it's in the book. We already know. You've got to tell us anyway. So how many times? And he says 42. And he looks, he says, 42? He said, yeah, 42. St. Peter says, it's a miracle you got into heaven. He says, I don't know how it happened. It's great. I'm happy. And so he says, well, what kind of car am I going to get? He says, well, you know, for that kind of record, you're not going to get a good one. And this guy's about 6'6", and what appears as a tiny little Mini with flat tires, broken windscreen, the door doesn't work, it's kind of jammed, you have to bang it open to get in. And he squeezes in and he drives away. And the next day they're at the traffic lights and the Scots guy pulls up in the middle and the American and the Englishman pull up either side and they look towards the Scottish guy and he's crying. These poor guys, his eyes, he's pouring new tears. And the Scots guy looks at him, the American guy looks at him and says to him, what are you crying for? Look at the car I've got. And the Scots guy said, yeah, but I just saw my wife and she's using roller skates.
Good one.
You like that one, Christian? I
That's
can
a
see
good
you
one.
smiling, so I'm assuming you like that one.
Absolutely.
Okay. I think it's late on in the day. I got a much better reaction on my earlier class today, but I think, God, I understand that. By 7:30, your brain is maybe, takes a little while for it to absorb. That joke is funny, by the way. I'm just putting that out there. Okay. I wish I had more time. It's kind of funny saying that when we've got 3 hours and 40 minutes, but time does fly. To go into more detail, but at least I've given you the gist of what you need to know. So when you've got questions and they mention to you solve using the substitution method, you feel comfortable about the x equals y equals part, and then you do the question, right? I have lots of examples on my notes that you can go over if you need to see more practice, and you can certainly contact me on and off. I won't be, you know, you've got until Sunday midnight to do these questions. So I will look at my email occasionally, but I have family coming over for the 4th. So I may not be, you know, I might take a couple hours to get back to you, but I will get back to you. So who's the last method? Well, the last method is called the elimination method, or the addition method. I actually prefer the name the addition method. Mostly because the addition method gives you a better idea on how this thing gets solved, how this system of equation gets solved. So let's show you what a question might look like. Here is a good old-fashioned system of equations, right? We're trying to solve, I mean, that's all today's been about, right? Solving system of equations from start to finish. That's what we've been doing, right? So here is a system of equations, and we're going to solve it using the elimination stroke addition method. Now, the way this method works is kind of tricky, but once you get the gist of it, it's actually kind of cool as well. What you need to have is the two equations have to have a very special shape to them. Each equation should have the same number of x's or y's, but one of them should be positive and the other should be negative. So if you can get a situation where this is true, as it is here, what you can do, and that's why I like the name the addition method, is that you can add the left-hand side equations together and you add the right-hand side together. Well, when you add the right-hand side together, you get 15. Now, what's going to happen when you add these two guys to these two guys? Do you see that because this is plus and this is minus? Oops, my earphone has just said battery low. I hope it lasts long enough. Can you see that these two are going to eliminate each other? I guess that's why they call it the elimination method. Do you see you make it happen by adding? That's probably why it's called the adding method, the addition method. So what are we left with? Oh, 5x equals 15. It's almost like they're handing the solution to you on a plate, aren't they? Because one more line and we're done. Sneaky. Right. Now, we're only half done. Don't we now need to find out what the second part of the solution is, what the y value needs to be? So I am going to put x equals 3 into equation 1 or equation 2, whatever one you feel like, doesn't matter. I'm going to put it into equation 1. So equation 1 says that 2x take away y should equal 10. But since I know x is 3, I now have 6 take away y equals 10. There are a couple of ways to solve this thing. I mean, you can just keep doing the usual subtract things from both sides. And if I did that, you would get, and then divide both sides by -1. And some people, when they get to that line, just do it in their head. Isn't 6 take away -4 10? So the answer is y was -4. So there's your solution. X is 3, y is -4. It's quite different from the other method, at least the beginning of it, isn't it? Right? You add two equations together rather than do any kind of substitution. Let's try another one. Now, again, this is meant to be one of the easier versions. Would you agree that these two equations are good to go? Only in this case, you see, it's the x's that are equal. One's plus and the other's negative. That has to be true for the addition method to work, right? You need the same number of x's, 1 plus and 1 minus, or the same number of y's, 1 plus and 1 minus. Now, if that's the case, which it is, then you can add. And when you add them, you get 12. You add these, they kill each other off. You add these, you get 2y. That makes y equals 6. Right, so it's got 1/2 of the answer. And then you put y equals 6 into any equation you like. Would you want me to do this time? 1 or 2? I don't really think it matters to me, but just give me a number and I'll do it. If you want me to put, say the number again?
1.
1 it is, okay. So 3x take away 2y is 10, becomes 3x take away 2 lots of 6, which is 10. 3x take away 12 is 10. 3x is, add 12 is 22. X is not very pretty answer. So our solution will be 22/3, 6. But you see, the algebra doesn't care. Are we comfortable with this process, at least as far as it goes? As long as you have 2 x's, 1 plus and 1 minus, or 2 y's, 1 plus or 1 minus, this is good to go, right? Now, the reason that these two have solutions is because they cross at a point, right? What does this method look like when you have parallel lines, and what does this method look like when you've got the same line, right? What does the math look like in those two situations? Because sometimes aren't you going to solve it and the answer is 0 solutions, right? No solutions. And sometimes you're going to solve it and the answer is going to be infinite solutions. Parallel lines get you 0 solutions. the same line on top of each other gets you infinite solutions. So let me show you what the math looks like when that does happen. Suppose you have 3x take away 6y is 10. And negative 3x add 6y equals 2. Now, can you already see that something weird is going on?
They're going to cancel out.
They're all going to cancel out, right? And you're going to get a 0 on this side, and you're going to get a 12 on that side. Okay, do you think that means parallel, no solution, or the same line on top of itself, infinite solution? What do you think that means?
Infinite
No
solution.
solution.
No solution. Parallel lines, no solution. Why is there no solution? 0 is never going to equal 12, is it? Right? It's a falsehood. 0 solutions because it's never going to be true. Now, you can imagine that's not very, well, that's kind of quick, isn't it? If that happens, it's going to be a really short question, right? You're not going to do a lot if that happens. The next one is even weirder. Here are our two equations. When you add them together, oops, you get 0. Kill each other off, kill each other off. You get 0 equals 0. 0 equals 12 is never true. No solutions. Isn't 0 equals 0 always true?
Yeah.
Infinite solutions. And you're saying, why does that happen? If you actually sketch those, you'd get the same line on top of itself. Now, there's only one other feature that we need to kind of fix here, and that is they're not going to be nice to you in every question and give you them all set up, ready to be added, right? Like here. They're more likely to give you a question where you've got to work at it. And that's the part that makes this a little bit trickier to do. So let me show you an example of this happening. There we go. As these two equations stand right now, would you agree that adding them is not a good idea? Why? Because these are different amounts and these are different amounts. And to make the addition method work, which is the preferred name, right? They call it elimination. But to make the addition method work, don't you have to have 3x and minus 3x, or 4x and minus 4x, or 2y and minus 2y, right? You have to have 1 plus and 1 minus and the same number. So if they don't give you it, you make it happen. I am going to take equation 2 and I am going to multiply it by 2. You will not be able to hear me now. So if you hold on a second. I have a backup one. I hope this has got power in it. No.
Okay. Multiply by 2.
Thank you.
For any of you guys who are away from your computer and have like your thing off, he's starting again.
That's if they're paying attention.
Fair.
Not yet.